An extraordinary event is unfolding at this moment. Come September 2025, our planet will encounter a barrage of close encounters. The asteroid known as 2025 FA22 will glide by at roughly twice the Moon's distance, whereas 2025 RJ2 comes within under 300,000 kilometers. Numerous tinier bodies are cataloged crossing sublunar paths during one unprecedented week. Simultaneously, the oddball interstellar comet 3I/Atlas, with its unusual chemical makeup, hurtles toward Mars along a path unseen in the Minor Planet Center's records. These occurrences stretch the bounds of chance. Could this be mere celestial luck, or might it signal a trend that reshapes our strategies for protecting Earth? The resolution could alter our role as mere observers in the solar system. The month of September 2025 brings a relentless series of warnings. Experts at the Minor Planet Center record asteroid 2025 FA22 passing at about 2 times the lunar distance, around 835,000 kilometers away. Just 3 days prior, 2025 RJ2 zipped even nearer at a scant 0.78 lunar distances, or below 300,000 kilometers. Such incidents aren't happening in isolation. From September 12th through 18th, the tally breaks every historical benchmark. No fewer than 28 near-Earth objects venture inside the Moon's orbit. That's 3 times the previous weekly peak. The majority measure between 8 and 25 meters, objects capable of burning up on re-entry or detonating akin to the Chelyabinsk incident. Yet FA22 and RJ2 stand out as substantial threats warranting worldwide scrutiny, with sizes potentially reaching 120 meters across. Every spotting lights up monitors in monitoring networks. From Pan-STARRS in Hawaii and Atlas in Chile to the Vera C. Rubin Observatory in Chile's Atacama Desert and the Catalina Sky Survey in Arizona. Information pours in from robotic scopes, sifted by algorithms designed to spot the dimmest, swiftest specks. The rhythm shows no mercy. Fresh finds get identified, followed, and entered into databases often mere hours after initial detection. The Rubin Observatory, fresh from its operational debut months ago, unleashes a torrent of new insights. Its expansive imaging system scans vast sky sections in broad sweeps, capturing transients that evaded notice only a year earlier. By the numbers, such a flurry should occur only every few decades. Adjusted models accounting for observational biases estimate the likelihood of over 25 sublunar NEOs in 1 week at under 1 in 1,500. Despite enhanced spotting capabilities, the September uptick remains anomalous. It forms a grouping that bucks the typical haphazard distribution of asteroid flybys. A few specialists ponder gravitational alignments or an unseen fragmentation in the main belt, though most attribute it to cutting-edge tools. Now, spotting rates top 90% for bodies over 20 meters within lunar range. Gaps in coverage are narrowing, yet persist. Trajectories from the sun's direction still pose challenges, a hard-learned truth from the Chelyabinsk explosion over a decade ago. Online, these figures spark wild theories. Graphs spread depicting a peak too pronounced for randomness. Some label it coordinated, a cosmic alert, others propose. Among researchers, responses stay cautious yet vigilant. Every near shave gets documented, scrutinized, and stored, bolstering a defense network whose strength hinges on the most recent finds. For a fleeting span, global focus turns upward. And the query persists: what if one of these had veered just a bit nearer? Picture if FA22 had hit its mark. Spanning 120 meters, about the length of an urban block, the rock would start its plunge from the upper atmosphere, a quiet racing at more than 18 kilometers per second. Assuming it's rocky, as many of that scale are, it would squeeze the air in front until immense forces tore it apart in a fierce atmospheric blast, echoing the 2013 Chelyabinsk event. But magnitude counts. Chelyabinsk's pressure wave shattered panes in 6 towns and hospitalized over 1,500 individuals, mainly from lacerations and head injuries. FA22 packs over 20 times the punch. Such a rocky body might detonate between 10 and 20 kilometers up, unleashing force akin to multiple megatons of TNT. The resulting blast would level structures over vast areas in square kilometers. Those in the vicinity of Ground Zero would have mere moments to respond. Windows would explode, barriers would crumple, and the thermal pulse might set roofs ablaze. The ruin wouldn't stay confined to the impact zone. Surrounding districts would suffer from hurled rubble and failing edifices, amplifying the peril. Should Fa-22 consist of iron, the outcome shifts dramatically. Iron variants pack more density and hold together better. Rather than breaking up, it might bore right through the air layer, slamming into the surface at almost undiminished velocity. That would carve a pit hundreds of meters across, spawn a blaze seen from afar, and hurl debris high into the upper atmosphere. Regional damage would wreck key systems, while broader ecological effects could extend much farther based on the site. Consider now an oceanic strike. More than two-thirds of likely collision points lie over water. In that case, the force would generate an enormous vapor cloud, and a barrage of tsunami waves would spread out from the impact site. Although much of the surge's power fades rapidly in the ocean depths, shorelines within several hundred kilometers might encounter towering walls of water reaching tens of meters tall. Harbors, urban areas, and vulnerable atolls would suffer devastating inundation with scant prior notice. The Chelyabinsk incident highlighted this vulnerability. Incoming objects from the sun-facing side remain hidden from Earth-bound observatories right up to the final seconds. Sergei Karpov, famous for his dashboard camera video that captured the chaos of that day, continues to recount the destruction through sounds of shattering, broken windows, and utter disarray. These days, he collaborates with emergency preparedness groups, pushing urban planners to practice responses for surprises that arrive unannounced. His core advice boils down to this: the boundary separating a benign meteor streak from a metropolis-destroying catastrophe is far slimmer than people imagine. Post-event modeling after every near-miss reveals grim figures. Collision force, local population concentration, and hour of occurrence. All factors in an impartial celestial calculation devoid of purpose or cruelty. The sole safeguard lies in constant alertness, prompt identification, and frameworks that convert alerts into swift measures. Absent those, the toll registers in ruined urban centers and destinies irrevocably altered. Swan offers a contrasting display of celestial drama. Spotted on September 11, 2025, not through a visual scope, but via the Solar Wind Anisotropy Swan device on SOHO, the comet's emergence was heralded by an abrupt increase in hydrogen output. The Lyman alpha glow, a UV signature undetectable without aids, illuminated sensor feeds well before terrestrial spotters had a clue where to search. A few hobbyist astronomers probing the Virgo region verified the orbital probe's suggestions. Swan was intensifying rapidly, its tail extending twice as long in just one evening. This went beyond mere luminosity. Spectral analysis showed a gas envelope heavy with volatiles, led by hydrogen alongside traces of cyanogen and carbon molecules. The release of gases surged as the comet approached its solar closest point, with hydrogen output exceeding water vapor by a ratio that surprised veteran skywatchers. The cause? Swan's frozen core was splintering from solar warmth, unveiling new surfaces and unleashing pent-up chemicals through repeated eruptions. Every fresh fissure in the core triggered another hydrogen burst, detectable only by UV-sensitive gear. Major facilities rushed to book additional viewing slots. The Rubin Observatory, adjusting its scanning rhythm, allocated urgent slots to monitor the shifting envelope. At the same time, amateur enthusiasts kept supplying inputs to the data flow, clocking eruptions, charting tail shapes, and noting abrupt luminosity drops. Their notifications guided precision spectrometers toward ephemeral features. Streams of ejecta curving from the heart, minor variations in composition, and indicators of internal strain that signal impending disintegration. As September progressed, the chance of splitting grew pressing. Updated predictions indicated Swan's core, pocked with fissures, could fail to endure its solar grace. Should it disintegrate, the scattered fragments might create a dazzling vista observable from ground and orbit alike. For asteroid defense specialists, Swan's erratic nature underscored a key lesson. Dangers don't always follow quiet, foreseeable routes. Occasionally, the alert arrives as an explosive hydrogen signal, with initial spotting reliant on a worldwide cadre of volunteers equipped with scopes and detectors aimed skyward. Every planetary protection schedule marks April 13th, 2029, in bold red. That date brings Apophis skimming a mere 32,000 kilometers above Earth's crust, nearer than numerous telecom orbits, and plain to see without binoculars as it arcs overhead. For a long stretch, Apophis fueled apocalyptic news stories, labeled a world ender when first noted in 2004. Yet over time, collision fears have receded, giving way to an exceptional research chance. It's essentially a public drill for threat mitigation under global scrutiny with tools primed. The flyby transcends mere visuals. Our planet's pull will stretch toward Apophis, stirring upheavals not in oceans, but in stone and grit. Experts anticipate observable alterations, crustal slides, surface rubble dislodged, perhaps even a reconfiguration of the rock's profile. Such gravitational strains have never been gauged so intimately on an object of this scale. It amounts to an unplanned cosmic test no facility can replicate. To record it, NASA launched OSIRIS-APEX, a probe set to link up with APIS shortly post-pass. Its objectives include logging each mark, repositioned stone, and hint of our world's unseen influence. Comparative images from before and after will disclose how space rocks react to intimate brushes and how minor tugs alter a drifter's path. To Andrea Riley, a key engineer on the HERO squad, the event holds deep personal resonance. In a 2022 journal note, she remembers the unease of following Apophis coverage in the media during her teenage years. That mix of apprehension and excitement over emerging tech now drives her efforts. APIS goes beyond a mere challenge for researchers and probes. It serves as a vital practice run for humankind's capacity to monitor, simulate, and potentially redirect an actual hazard if required. Each computation, each measurement, every program developed for OSIRIS-APEX or terrestrial radar contributes to a tomorrow where near misses are handled with steady expertise rather than alarm. While APHIS hurdles by, observers worldwide witness planetary protection at work, transforming a once terrifying news story into one of readiness and exploration. The Comet 3I/Atlas, designated C/2025N1, distinguishes itself right from the initial analysis. On July 1st, Pan-STARRS detected its hyperbolic trajectory, yet the molecular signature prompted astronomers to vie for access to the planet's biggest observatories. Preliminary VTX shooter observations, obtained as the object traversed roughly 4 astronomical units, indicated a coma primarily composed of carbon dioxide rather than water vapor. JWST verified the findings in August. The carbon dioxide output measured 129 kilograms per second, with water production lagging significantly at only 6. This creates a ratio close to 20-1. Such a pattern is unheard of for a comet so luminous and dynamic. By contrast, typical comets in our solar system invert that proportion, with water release vastly exceeding carbon dioxide. In this case, the standard dynamics are upended. The oddities extend beyond the gases. Detailed spectra from the VT's UV tool, gathered across multiple evenings in July and August, revealed a robust atomic nickel emission reaching 4.6 G per second from the coma by August 21st. However, iron, which typically accompanies nickel in cometary compositions, remained undetectable, below the instrument's sensitivity. This iron-free nickel profile is uncommon, even for objects from beyond our system. Among local comets, nickel and iron usually emerge in tandem, released through identical solar heating mechanisms. Explanations vary from distinctive origin processes to the gradual depletion of iron over eons of interstellar travel. Some researchers suggest the disintegration of nickel-laden organic materials. Others propose cosmic ray erosion, preferentially removing more fragile iron substances. No unified theory accounts for the observations so far, though discussions remain heated and unresolved. In mid-August, yet another twist emerged. The Mars Reconnaissance Orbiter, operating in ultraviolet bands, recorded an abrupt surge, a burst that intensified the comet's glow by double within under 36 hours. Telescopic imaging from Earth displayed the tail fragmenting into distinct streams, with dust flowing along divergent paths. These intermittent surges diverge from the familiar water-fueled sprays. Rather, they suggest reservoirs of carbon dioxide or similar substances bursting forth as solar rays infiltrate new cracks. Investigations into its spin deepen the mystery. Photometric light curves imply a leisurely, perhaps erratic rotation with an axis that varies periodically. The cycle exceeds 22 hours, accompanied by subtle luminosity shifts. This points to an almost round core or intricate, non-axis aligned tumbling. Such traits complicate forecasts for surges and tail patterns. Every fresh batch of information uncovers more fascination. And as perihelion approaches on October 29th, global spectroscopists are in a frenzy to document each nuance before the comet vanishes solarward. At present, 3I/Atlas endures as a compositional enigma, a leisurely rotating envoy from the galaxy's chillier, more obscure realms.